Hi everybody, welcome to Distributed Transactions in Yugabyte. I am Karthik Ranganathan, one of the founders and the CTO at Yugabyte, and we're going to dive into the under the hood on how distributed transactions work with YugabyteDB. Okay, first off, what is YugabyteDB? YugabyteDB is a transactional high-performance database that is ideal for building planet-scale cloud services. It brings together NoSQL and SQL into a single database that is built in a cloud-native fashion. Okay, so with that, let's jump right into how YugabyteDB handles distributed transactions. Recall that RDBMSs typically handle transactions on a single node. By virtue of Yugabyte being scale-out, it needs to coordinate a transaction in an atomic fashion across multiple nodes. Okay. So the first few things you need to know about Yugabyte is that it has a distributed transaction manager, and it has the distributed transaction manager ensures that any tablet server or effectively node can execute and coordinate an incoming distributed transaction. The second piece is it has a distributed transaction status tablet, which keeps track of the current status of all the active transactions. And thirdly, every transaction in Yugabyte can have one of three statuses. It can be pending, it can be committed, or it can be aborted. A committed transaction is visible to the end user for reads. An aborted transaction effectively never happened, so it throws an error to the end user and is rolled back. And a pending transaction is currently in progress. Okay, so let's dive right into the write path of transactions. Now, let's take the example of an incoming transaction or a query that hits a transaction manager. A transaction manager lives on one of the nodes, in this case, the tablet server number 1. The client tries to change two keys to two different values in an atomic fashion. It's trying to set key 1 to value 1 and key 2 to value 2. Now, by virtue of it being a transaction, this entire operation should happen atomically or should fail. Now, the first thing the transaction manager does is it creates a status record for this transaction in the distributed transaction table. That makes sure that this transaction is now tracked. Of course, when the status table is created, it is created with the transaction in pending status. Okay, now enter a couple of other tablet servers. Now, the writes for each of those keys, key 1 and key 2, should happen to two different tablet servers or nodes in the most general case. So the transaction manager writes a provisional record, which is not visible to other reads yet, but tells the database that this update is in progress. It writes the update for key 1 to tablet server 3 and for key 2 to tablet server 4. Once it has successfully written its provisional record on all of the keys required to be updated for the transaction, it then goes ahead and commits the transaction. It does so by flipping the status of the transaction from pending to completed. Okay, and at this point, since the transaction has been written in a durable fashion and end users can now start to read the transaction, the client gets an acknowledgement back saying that the transaction was committed. Now, recall that we still have a couple of provisional records written on some nodes, and every time a read hits these nodes, they would have to go to the transaction status table to figure out the actual state of the transaction. In order to avoid this two-hop read, the system YugabyteDB flushes the state of the provisional records down to update the values to have final records, so that every future read can now do a direct read and not have to hop to the transaction table. Okay, so that was a brief, quick overview of the write path. Now let's look at the read path. Of course, we're simplifying things here, but there's a number of other concerns to keep in mind when reads come in and writes come in, such as what are the isolation levels and how do you optimize writes if they don't touch multiple keys, or how can you reduce the number of hops to gain more performance, etc., etc. But once again, let's look at a simple view. In the read path, let's say we're trying to read two keys, K1 and K2, the very two keys we updated in the previous example? Well, the first thing that happens is we pick a timestamp to read the data at. And this is extremely important because the updates to different nodes as a part of a single transaction, the write path, could happen at different times. And we need to be sure that we are reading at a particular point in time. So we pick an HT read or a hybrid timestamp on the transaction coordinator or manager, and we go ahead and perform the individual reads from different nodes. Now, if we find that there are no intents, we can go ahead and serve the value. But if we find that there is a provisional record that's been written into any of these keys, then we'll have to go to the transaction status table and we'd have to figure out the actual state of the transaction. Now, the state of the transaction could say it is committed, at which point we include the value. It could say it's aborted, at which point we ignore the value. And it could be pending, and here's where you have to resolve the conflict because we're potentially trying to read a value that's trying to be updated according to the isolation level of the read request. Now, assuming that we were able to find the value committed, we would be able to respond to the client by reading and including the latest value or appropriately. Okay, so with that, let's jump into a quick demo. I'm going to pick up the distributed transactions from our Yugabyte docs, and we're going to walk through a bank account example. We're going to have a couple of people that have a checking and a savings account, and we're going to transfer $200 from one person's checking account to another person's checking account. So here's our distributed transactions documents page. Now we're going to walk right down and connect to this system. So all I've done in a command prompt right here is I've downloaded and installed the latest version of YugabyteDB on a local machine. So all I've done here is I've installed a local node version of YugabyteDB, and I'm going to create a local cluster. Okay, so with that, I have created a local cluster. I'm going to connect to it using CQLSH. All right, now let's go ahead and walk through some of these examples. We're first going to create a banking key space, and then we're going to create a bank accounts table with transactions enabled. Note that in this example, we have the account name as the primary hash key so that each user has an account. We're just using the username in this example to simplify things. And there's an account type, which is also a part of the primary key, and this represents a checking account or a savings account. And finally, there's a balance, which is literally what is the balance in that account. Okay, so let's go ahead and insert some sample data. Now, having inserted that data, I should be able to select it all back and see that there is a person, John, that has a checking account with $100 and a savings account with $1,000, and another person, Smith, that has a checking account with $50 and a savings account with $2,000. Okay, let's go further. We should be able to do simple things like select the entire balance for John, which is about $1,100. Now, let's execute a transaction. Let's say John wants to transfer $200 to Smith. The first thing he does is he initiates a transaction where he transfers $200 from his savings account to his checking account because he doesn't have $200 in his checking account. So it's as simple as writing a begin transaction and then doing the individual statements and doing an end transaction. Okay, we should be able to verify this by just selecting what John has in his accounts, and we find that he has indeed transferred the $200. Now, let's go further and get John to transfer $200 from John's checking account to Smith's checking account. So we're removing $200 from John's account and adding it to Smith's account. Okay, that went ahead and got executed. Now we should be able to go ahead and figure out what just happened in the system. We find that John no longer has the extra $200, and Smith went from $50 to $250, so the data got transferred. And also equally interesting is the fact that if you look at the internal database's write timestamp, you find that the timestamps for John's and Smith's entries are exactly the same. All right, so now we would be able to run our higher level queries which figure out what is the total balance in all of John's accounts, and a similar query that tells you what is the total balance in all of Smith's accounts. Okay, so what we saw here is an example of a fully decentralized and scale-out architecture for distributed transactions that does not have a single point of failure. So if you want to scale out the number of transactions, just add more nodes. It's as simple as that. Okay, quick talk about how we achieve performance. So recall that Yugabyte is transactional, but it is also highly performant. We employ a number of strategies inside the database to increase its performance. Things like aggressively caching information about transactions that are in progress, doing fine-grained locking for concurrency control. So we figure out what are the various types of operations that can overlap with each other and really optimize those. We also do safe time tracking, which is a topic in itself. But the point is, for every read issued by the user, if you want to know the authoritative value of a single key value, we do not issue a quorum read. We just go and read it from the leader. And finally, we auto-optimize single row ACID transactions to be extremely fast, while distributed transactions have consistency. Okay, stay tuned for benchmark results. We're working on these. We have some exciting results to share with you on the performance of distributed transactions. Quick call out on what's next. We have verified our distributed transactions using Jepsen. Our blog post just went live recently. Take a look at it and see how we ensure that our transactions are absolutely ACID compliant. And finally, if you want to try it out, you can always go to the quick start guide and just install and do whatever I did from the documentation. Thanks a whole lot for watching, everybody. We'll be back with more.